Hey folks, welcome back for another episode of Code Club with this live stream here on the Riffomonas Project YouTube channel. Sorry for some initial technical difficulties there. I really appreciate you joining in. If we haven't met before, well, my name is Pat Schloss, and I am a professor at the University of Michigan in Ann Arbor. And I just really get excited about data visualization and helping others to recreate their favorite data visualizations in the R programming language. And so my goal for today is to work with you to recreate this set of panels that was recently published in a paper in the journal Nature. The lab that this came out of was from Cynthia Sears at Johns Hopkins University, and there were other collaborators, but she was the senior author on that paper. And what they're interested in is the role of gut microbes in driving colorectal cancer. And so her lab over the years has been very interested in Bacteroides fragilis, so B-frag as we call it. And some versions of B-frag produce a toxin. And the toxin-producing ones are thought to be a driver of some forms of colon cancer. And so in this paper, what they were looking at are the host factors, the receptors that cause the toxin to be toxic. And so as we can see here in panel B, they have these dose response curves where on the x-axis, they're putting various concentrations of B-frag toxin, BFT, with these 4 different genotypes. And looking at E-cadherin, for some reason I have such a hard time saying that, on the y-axis. And so basically, as that drops, the cells are sick and dying. And so one of the metrics that they look at for the effectiveness of a toxin is the IC50. And so what they did is they fit this data, and each point here represents 3 replicates. And so they fit a nonlinear curve to this that allowed them to ascertain the 50% knockdown level, or the IC50. And that IC50 then was plotted over here in panel C as a dynamite plot on a log scale. So what I'm going to do is I'm going to recreate panel B, and I do not like panel C. I didn't talk about panel C in my critique video, which I'll come to in a minute, but I'm going to recreate panel B and try to integrate the information from panel C into panel B. And so, as I was saying, this is the Riffomonas YouTube channel. If you want to get my newsletter that comes out once a week, you can go to riffomonas.org, which I will paste here in the chat, and would love to have you join my mailing list down here. It's once a week, very low spam, hopefully very high content, where I try to talk about some data visualization I have found in the literature at a very high level. And so this past week, I talked a little bit about last week's plot again, but then also you can see this plot in here. And so I'm going to go ahead and paste this in so you can find that link. And something else I talked about in this week's newsletter, a little bit of self-promotion, which was that I would love to work with you to help improve your data visualization on a one-on-one level, or perhaps with your research group. And so if you're interested in the type of stuff that I'm putting on this video and would like to see it applied to your own work to help you, by all means, shoot me an email at pat@riffomonas.org. One of the problems with these videos is that it's a bit like an autopsy, right? Like, we see the plot, it's been published, there's nothing we can do about it. But wouldn't it be nice if there was something we could do about it, right? What if we could go back in time to make a better plot that you could then publish and do a better job of conveying information to your audience with? And so that's what I would like to do for you, right? And perhaps meet via Zoom once a week or every other week, or however often would work well for you to help you make more effective data visualizations. Okay, so aside from the newsletter, I also put out these critique videos that I posted on Monday for this particular plot and set of plots. So you can see they have panel B and C here. There's also panel D and E, which are very similar types of plots. I don't know that I will get to panels D and E this week, but certainly B and C we will be talking about. And so I'd encourage you to go back and watch this critique video later to get a sense of how I try to do a constructive critique. And as I mentioned, the paper that we're going to draw this figure from was published just last week, actually, in the journal Nature. And again, titled a pro-carcinogenic bacterial toxin binds Claudin-4 to cleave E-cadherin. And if we look at the figures, again, the figure we are interested in here is figure 2. And we can see all the figures, right? So there's G different panels here. Again, I'm going to focus on panels B and C. And if we have time, we might get to D and E, but hopefully you can see they're very similar to each other. In the critique video, I really focused on panels B and D, mostly on panel B. But as I said, I would like to think about bringing panel C into panel B somehow, okay? So my plan is to first, and I think I've got a zoomed in version here. My plan is to initially recreate panel B, okay? And so let's do that first. We'll look at the data that's being plotted in panel C, and then we'll think about a couple different ways that we can draw those together, all right? So again, my plan is on these videos to typically go for about 2 hours. Got a little bit of a late start today, so but total about 2 hours. So let's go ahead and get going with that. And I have an RStudio session open here, which you can see behind me. I'm loading the library tidyverse, the library read Excel, because the authors were gracious enough to make their data available through the Nature website as an Excel workbook. And then I'm going to save this figure more or less in the same dimensions as what the authors originally published it as, okay? And if you want to get the code that I'm generating, then at the end of this episode, you can go down below in the description and find a link to a blog post where you can get the code. All right, and so once I'm done with the live stream, I generally get that up within the next hour after finishing the recording. All right, so let's head back to this page. And again, if we scroll down to the bottom, we can see the source data. And again, this is figure 2. And so this link will take us to another link for source data figure 2, that if you hover over and look at the bottom, it's probably too small to see on your screen right now, but that is an Excel workbook. So I'm going to go ahead and copy that link address. And now let's come back to our RStudio session, and we'll do download file. And that's going to take a URL and a destination file. So let's go ahead and call this figure 2 XLSX. And the URL is going to be this monster, really long URL. And so then when I download that, and we look over in the Finder tab, File tab in RStudio, we can see figure2.xlsx appear there. Okay. So we now have the file, and we saved it as figure2 read figure2.xlsx. And so let's go ahead and open that up. And nothing to open the document. That's odd. I misspelled this. XL. Wait, did I misspell it? I'm kind of caught off guard here that this isn't working. XLSX. That's right. I downloaded it as the wrong name. So let's go ahead and re-download it correctly. So I think my local computer is trying too hard to match the ending of the name with the application that we're trying to open. And so let's take a look at this now. So this is the Microsoft Excel workbook, and oh, it's trying to open the App Store. Go away. All right. So again, we're going to be looking at panel 2B, and panel 2D we can see is like similar type of information. The panel 2C, it's good to know this is here, but I'm going to ultimately get this data, I think, out of the curve fit is my plan, okay? And so, yeah, so we can see this table is not tidy, and so we need to do a bit of work to read this in and get it into a tidy format so that we can then plot it, do a curve fit, and do all the other great stuff we want to do. All right, so as you are logging in or kind of getting adjusted here, we will start to speed things up here in a moment. But I'd love it if you went ahead and introduce yourself and tell us where you are from, and yeah, just tell us where you're from. And I always get a rush out of seeing the diversity of places that people are logging into from around the world. So we have loaded read Excel. Actually, did I load it? No, I did not load it. So let's go ahead and load the tidyverse and read Excel. And then I can do read Excel. And we'll do figure 2.xlsx. And so this, I'm having problems with spelling today. Excel. And so if we read Excel, just like I did there, then this is automatically, by default, going to read in the first tab, right? So this figure 2b, and it's going to do its best to read it in. But if we look at the workbook, we see that in cell A1 is the title of the page, which is not what we want. And then we see that the data column headings start in panel 3. But these are kind of funky column headings, right? So they're like, this wild type is basically, they took 3 cells next to each other, left to right, and joined those or merged them together. And so when we look at how it's reading it in, we can kind of see that down here, right? There's like wild type, NA, C4KO, NA, and so forth, right? And so I think what I'm going to do is let's go ahead and do sheet equals fig 2b. And that isn't going to change anything, but I like to be more explicit about what's going on. And then let's do skip equals 2. And this then will make that our column names. And what I want to do is give it column names. So we'll do call names equals, and let's go ahead and do BFT as a column name. And then we're going to have wild type as a column name. But with wild type, we've got 3 replicates. And so I think what I'm going to do is use the glue package. So we'll do library glue. And so what I'm envisioning, let me go ahead and just take this vector here and show you what we'll do. So if I do this, I get BFT and wild type, right? But if I do glue on wild type and do like underscore and then curly brace 1:3. So that 1:3 will give me a vector of 1, 2, 3. And then this glue with the wild type underscore. I have to load the library. I'm so excited to use the tool. I forgot to load it. All right. And I need a closing parenthesis. There we go. So that then gives me wild type underscore 1, wild type underscore 2, wild type underscore 3. And the benefit of doing that, of having like wild type underscore some number, is that I can then create, so this is a wide data frame, and I want it to be long, right? And so I should be able to make a column that has the BFT, the concentration of the BFT, and then pivot longer will pull apart these column names for the genotype and the replicate. And I should be able to pull it apart on that underscore, okay? So we'll do, again, glue on C4 underscore 1:3. And then we'll do another glue. I think this one is on C3, 1:3. And then we have this C4KO complemented with GFP, with a GFP tagged version of C4. So I'll go glue GFP underscore 1:3, and that has to be in curly braces, right? And so then if we look at that vector, we get our column names. So I'm going to go ahead and take this vector, and let's put that in for our column names. And when I do this, I think I always forget if I need to skip 3 lines or 2 lines in the way I'm doing this. So it's very likely that I might need to modify that skip argument, but that's fine. No big deal. Yep. So what we see is we get the column names I made, but it left in the old column name. So I need to increase that skip to 3. And so now what we see is that we incorporate those column names. And so we see that it is starting at 20 here, right? And so here, it's a little formatted odd, but that is also 20. So we've got our data loaded in. Let's go ahead and put that parenthesis up there. And so now we want to pivot it longer, like I said, right? So we've got John from Barrington, welcome. We've got someone from Germany, and we've got Mark from Melbourne, Australia, not Florida. So welcome. And let's go ahead and do pivot longer. And we'll do everything but BFT. And so if I do that with the defaults, I'm going to get two columns. I'm going to get BFT, name, and value. And so name and value are the default column names for what was in the column names and then what was in the cells, right? So we can specify that because I think that would be good. And so we can do names 2 equals, and then I can give it 2 column names. Normally I do this with 1 column name, but let's try it with 2. So we'll do genotype, and then we'll do rep, and then we'll do name is sep, and that's going to be an underscore, right? And then we'll do values 2 equals cadherin, okay? And so now what you'll see is that we've got the BFT, the genotype, the rep, and the cadherin, okay? And so just like that, we've read it in from Excel, we've got it tidy, bam, we are ready to plot this, okay? And then we've got Karso from Indonesia, awesome. That's far away from here. So is Melbourne. So let's now go ahead and put this into ggplot. So on the x-axis, again, if we look at this plot, we're going to want the BFT concentration, and the y is going to be that cadherin, right? So one thing that I just want to briefly call your attention to that we'll obviously get into is that, in my opinion, there's no real geom here, right? In the final plot for panel B, we are not going to use a geom underscore function. That everything that's presented here is summary data, right? So we have the mean plus or minus the standard deviation. We have the curve fit. And so those are all statistical transformations of the data. We also have a statistical transformation on the x-axis, right? And so that's interesting, right? So let's go ahead and plot the data first, and then we'll come back and obviously get in those summary data. So on the x, we'll do BFT. The y will be cadherin. And then we'll also then do color equals genotype. And then let's start with geom jitter and see what this looks like. And I, like I said, saved this already to a PNG file that is similar aspect ratio of the original. And so what you can see is that we go from pretty close to 0 out to 20, but this is on a continuous scale, on a Cartesian scale, but we'd like it to be on a log scale. So let's go ahead and put it into a log scale. So to do that, it's easy enough. We can do scale x log 10. It's on a log 10 scale, right? And so now what we see is that we've got this on a log scale, and I think this cloud of points here that maybe I can highlight there, those are all the points at 20. So they've been jittered pretty far apart. Maybe we could do like width equals 0.1. And so that will then draw that in pretty nicely. And let me shrink these down a little bit so we can see both of them. All right. So, so again, we can kind of see the trajectory of the data, right? Like this red for the C4 up here is the same as this red actually down here in the red squares. And then the purple going through, the green is, the purple is the wild type, which is black down here, right? So we're gonna have to work with the colors, but we're on our way, okay? So let's go ahead and start in on those statistical summaries. And let's do that first with, well, let's see. Yeah, let's go ahead and do the statistical summary. So we'll do stat underscore summary. And the it's going to take fun.data. And this is the function we want to give it to summarize our data, right? And so we're going to use mean underscore SDL. And so mean STL, mean, man, the fingers are not working today. Mean SDL. And if I hide my face, you'll see that there's a selection of summary functions from hmisc. And so hmisc has a function smean.sdl. And so that then within stat summary is being mean underscore SDL. And so mean SDL, again, is HMISC SDL. And if we look at its usage, we see that it is going to plot the mean plus or minus the standard deviation. But by default, it's going to use 2 standard deviations. So we'll have to remember that. And maybe I'll go ahead and copy this over here for the time being. And let's look at the stat summary help. And so again, we want stat summary, where we've got the mapping, the data, kind of like every other geom. And then we've got a geom for point range and the position. So by default, it's going to give us a circle with a line going out. And then there are these fun functions. And let's see. So fun data is a function that is given the complete data and should return a data frame with variables ymin, y, and ymax. So that's what mean SDL will do. Now, I want molt over here. I want that value to be 1. And so there, I'm going to have to use fun args to set molt to be 1. Okay. So we'll come in here and we'll do fun.args equals, and that's going to be a list, right? And we'll do molt equals 1. And let's roll with that for the time being. I'm going to comment this out. And so now what we see is kind of see that our mean is a bigger circle than what we were getting with geom jitter, right? So geom jitter are these smaller circles like this small red one, whereas stat summary is giving me this slightly larger circle. And you can probably also see like that line coming up out of that red circle, or this purple line, right? And so that's the point range geom, where you get a point and then you get a range out from that. To replicate what they had, I need a confidence, an error bar, right? And so with the little hats at the top and bottom. So for the time being, I'm going to comment out the geom bar, so it's, or the geom jitter rather, so it's easier to see, right? And so those smaller points went away. And so again, I'm going to have to run stat summary twice, once for the mean and once for the error bar, okay? So in here, remember like one of the first arguments was geom. I can do geom point, right, like this. And so now what you see is I get those points. And something else that occurs to me is that I have varied the color by the genotype, but I also need to vary the plotting symbol by the genotype. So let's come back up here into ggplot and we'll do shape equals genotype. And there we go. Now we have 4 different shapes and 4 different colors for the data. And so Mark is saying, would you use geom smooth to get the line of best fit? Exactly. That we'll get there. Hang on. So that is the point, but now we also want the confidence interval, the error bar. And so let's now come back to the second stat summary and fix our indenting. And here the geom we want to use is error bar. Okay. And so that gets us our error bars. And right. And so I'm looking at that, and I think that looks about right, although those whiskers are really wide. We want them to be more on the order of the width of the plotting symbol. And so I think if I do like size equals 2, then I get size 2 circles and other shapes, right? And so now if I do geom error bar, can I do like width equals 2? Ah, that's too wide. So I thought maybe width and size might be the same. But if I do width equals 1 there, yeah, that's not going to work. Let's take this down to 0.2. And so that is much more on the scale of the size of the shapes, right? Cool. All right. And I think their shapes are a little bit smaller. So let's go ahead and take that down maybe to say like 1.5. And then let's make this 0.15. That looks pretty close in size. Hey, Lisa from Germany. Thanks for joining us. It's great to have you. And yeah, so we've got now our summary of each of the triplicates, right? And so, so again, I think that is really interesting, right? As like an effect where here they're not presenting the raw data. They're plotting a summary of the data. And I know like in my own work that I often have data where it's like, well, we want to show the data, but like if I do this, then like it's a hot mess, right? And perhaps I could do something like geom jitter. I could do like alpha equals like 0.2, right? To kind of make the points fade into the background. Something maybe a little bit darker than that, but you get the idea. But it's just jumbled. It's just a mess, right? And so I kind of like the idea of them using that summarized data. So let's roll with that for now, and I think that'll be fine. All right, so I'm going to go ahead and get rid of that geom jitter. I'll also get rid of this comment. And yeah, so again, here's where we are. So we've done one summary. Now let's do a second summary. Let's do that curve fit, okay? And then we'll come back and we'll go ahead and make everything look much more like what they have, okay? So let's think about that summary. So someone already mentioned geom smooth. And so if we run geom smooth, we get some output, right? So it's saying geom smooth using method loss and formula y tilde x. And so we get a fit through the data, right? That kind of looks like theirs. And it's using a loss function that I think is effectively like a polynomial kind of thing. And there's ways to kind of like play with the squiggliness of those lines. We could also do like SE equals false to get rid of the error bars around those lines. Perhaps we could also do like line width equals 0.2 to make those a little bit thinner. Maybe it'll go up to 0.3. And again, like the fit is kind of like theirs, but not really. And that's not really a parameterized model. Whereas what they're using is definitely a parameterized model that has as one of the parameters the IC50. So basically, what is the x-axis value that gives you a y value of 0.5? And that's what was getting plotted in panel C. Okay. And we've got Yakin from China, now in Germany. Great. Welcome. So again, we want to think about like, how do we improve this geom smooth? And so let's look at the help for geom smooth. And what we can see is that, yeah. So again, mapping data, smooth, position, method, formula. That's what we're going to end up using. We're going to change the formula to fit one of these dose response curve type of parameters. And then there's method, where there's LM, GLM, GAM, loss, or a function, like one of these. Auto is also acceptable, right? So we're going to use a non-linear fit through the data. And so we'll come back to that. So in the paper, let's see if I can find it. We'll look up dose response. I think they have a hyphen, dose response. Oh, they've got some weird hyphen. All right, I want to find where they mention it. There it is. Okay, so down here in the section E-cadherin flow cytometry, they mentioned that they, let's see, down here, right, curve fitting of the normalized surface E-cadherin values. sorry. Curve fitting of the normalized surface equidherent levels was performed in GraphPad Prism 10. We're not using GraphPad Prism. Using the model inhibitor versus response variable slope for parameters. And then fold resistance values were calculated by dividing the obtained half maximal inhibitory concentration values by the IC50 value of the wild type cells. Okay. And so what I did was I took this phrase and Googled it, and that got me to this page on GraphPad Prism. Okay. And so I will go ahead and paste that in. And let me look at some comments here. So Mark is saying, it looks like that I gave shape vector in summary. Last is inverted triangle. Right. So I haven't messed with the shapes yet. These are the 4 default shapes that come out when you use in Geom shape equals whatever, right? And so the first 4 shapes are circle, triangle, square, and plus. And we will be changing these as well as the order of the genotypes. But I want to get into the fit first. The other thing someone mentioned was can't you just turn down the smooth coefficient a bit and leave the formula as is? Span 2 gives a better fit. Great. So it sounds like someone's actually playing with this, which is fantastic. So if I do span equals 2, we get something like that, right? And so it's a different fit, right? So as you increase the span value, you are getting less squiggles, right? So if I did like span equals 0.2, oh, it's pretty upset with that, then I get like a perfect fit, right? It goes through all the points, but it looks pretty funky and it doesn't at all look like what they're doing. And this isn't a model that has parameters, right? So I want to be able to get out the parameter for the IC50 based on the model like what they did. Because again, I'm trying to reproduce what they did. So we will do that. So it's great to see that people are following along. I love that. That is just fantastic. So following, not just watching, but like running the code also. So let me come back to this GraphPad Prism page. So again, this is an equation that allows you to fit this model to data like this. And so one thing to note is that the x-axis is the concentration of the agonist, of the compound, the toxin, on a log scale. And so the top is for us going to be near 1 because they normalized everything between 0 and 1. So top will be near 1 and bottom will be near 0. So that's the top and the bottom. The IC50, again, is going to be that point right about there. That's midway between the top and bottom, or at 0.5, and that x position. And then the x-axis position. And then the hill slope is a value indicating kind of the slope of the curve. And so they say that the more negative, the more steep this line will be. But so this slope will be negative to indicate that it's falling off. Okay. So I'm going to go ahead and copy this model and I'll put it in here. And in stat smooth, I can then do formula equals, and I'm actually going to grab all this and plop that in here. And we'll do y tilde bottom and all this stuff, right? And then this x needs to be a little x. And then we're going to use method equals NLS for a non-linear fit. Yep. And then we're going to do formula. I'm forgetting my syntax here, so let's go back to the help. And formula, method. There's a way to give arguments, and that's probably in here somewhere. Method args. Okay. So let's look for method args. And so there's going to be arguments that we give to the method. And again, the method is, I'm starting to doubt myself. Is it NLS? Yeah, nonlinear least squares, okay? And so what we're going to give it is the start. And the start are the starting conditions. So we'll, again, do method.args. And that's, again, going to take a list. This is a lot like what we did up here with fun args, right? And we'll do list. We'll do start equals a list. And so then we're going to give it starting values for the bottom, the top, the IC50, and the hill slope. And so let's do bottom equals, I'm going to do 0.1, because again, if we come back here, none of these lines get to 0. There may be more like 0.1 or so. And then top, these are right at about 1. So let's make that 1.0. And again, what we're doing is we are giving the nonlinear least squares formula starting conditions for fitting the model, okay? And so then we need IC50, and that is going to be, I would say, right at about like 0.1 or 0.02. And then what we're going to want is the hill slope, and that I'm going to use of -1, because if we go back to the web page, they again point out that a hill slope more negative than -1 is steeper. And I think, yeah, so a hill slope of -1 is standard, they say here, right? So let's start with -1 and we'll go from there. And so when we pick these starting conditions, we want them to be close to what we think they should actually be. And a challenge here is that we've got 4 different lines that we're trying to fit, 4 different sets of data that we're trying to fit. And the 4 parameters here might not all work. The starting parameters might not work for all 4 data sets. So let's see what happens when we run this. And sure enough, failed to fit, failed to fit, failed to fit. And one thing I'm thinking is that, again, when I look at this page, the x-axis for the agonist is on a log scale. And so I think what I need to do for this IC50 would be to say like log 10 of 0.02 and see what that does. Oh, that's not happy either. And so when we get these like failed to fit things, then I think we kind of need to start tweaking some of those starting conditions. So let's try like 0.2 for the bottom. So that's not happy. If we do -2 for the hill slope, that's not happy either. Let me go ahead and turn off this, get rid of this span. That shouldn't really matter. So IC50 divided by X. We also need X to be log 10. Let's try that. Thanks for that comment. Okay. Now we just have warnings. Oh, more warnings. These were warnings also. All right, so this is unhappy. I think what would be better to do, perhaps, would be to actually fit the data with NLS so we can get a better sense that we're using the right model and we're using the right starting conditions. So I'm going to come back up here, and I'll break this apart, and I'm going to call this D for my data. And of course, that still gives an error. But if we do like, let's come in here and do D, which again, we get that data. And then we have, I'm going to go ahead and grab this formula and this argument stuff. And if we take D, let's start with like the wild type. So we'll do filter genotype equals wild type. This gets us all of the wild type data, right? And so then we can pipe this into NLS. And we have this formula, but here we have different columns, right? So we have e cadherin tilde bottom, and then instead of x, what we want is BFT. And for now, I'm going to take out this log 10. And then what we need to add is the start. And that is going to be this list. Okay. So I'm going to go ahead and plop that in. And I think I got the right parentheses. Okay, and then I forgot to add my data. So we'll do data equals period. And so that's going to be the data coming through the pipe up here is going to go into that data column. Okay. And so here it's still complaining, and maybe I will, let me make this 0.02. There we go. Okay, so we got it to fit. Yay! Okay, that's step one, right? And so what I get is 0.98 for top, which again is close to 1. The bottom is 0.14, which is, I think, close enough to 0.2. Our IC50 then is 0.05. And then our hill slope is negative 1.9. And so, yeah. So again, these are the parameters that fit the data. So now the challenge is let's turn this off for, well, instead of doing just one genotype, well, yeah, here's what we can do. Let's do C4. So that fits, right? And then C3, that doesn't fit. That's kind of a weird error though, but that gets us nothing. So what do I have for D? Oh, I have CD rather than C3. I am the typing is hard. Okay, so the C3 fits with these starting conditions. I can get rid of this. And then the GFP there, okay? So this is fitting, and I think what I changed was the IC50 and the BFT. And so we had IC50, let's turn this off. And again, we had like maybe I'll take this down to like 0.1, and then the top, we have like 1.03, 0.95, 1.02. So let's stick with 1. And then the log, the IC50, really kind of varied between like 0.02 or 3 or 4 or 5. And then as we see with like, I believe this is the C4, yeah, we get 1 point something, right? So I think this has to be log 10 for the IC50. So let's put that to be 1. And now let's see if this works. Nope, that didn't work. And 0.01, that doesn't work. Let's make some crazy number. No. So maybe this has to be log 10 on X. So I think one of the problems here, let's try this. I think one of the problems is the log scale. So let's turn off the log scale for just a minute. Aha, so that fits. But of course, it looks bad, right? So it fits when we don't use the log scale. And so, brave to work this out in real time. Thanks, Stephen. And we got Robert from Oklahoma. And let's see, Isabel, label, do you need to have label X as BFT and formula? No, so in this case, it's looking at Y and X. It's not using the BFT. I think that would give, if I did like BFT here, I mean, it's expecting BFT to be a parameter that I'm going to give it a starting value for. But if I give it X, let's give it back this, the scale X log 10 because we need that, right? So let's see. So I think X is going to be log 10 on X. And that is still not working. Okay. Let's see. So all right. So this should be working, but it's not. Let me do filter genotype equals wild type. And if you have ideas for what I'm not doing, holler. All right, so I know the wild type should fit with like these parameters. So I think the problem is in these values. And let's see if I do this. All right. Yeah, I can use DRM, but I don't want to use that because this works. I know this works because I had it working, and I don't want to cheat by looking at what I did before. So there is definitely a package to do dose response models, but that's not what I'm trying to do here. I'm trying to kind of work with scale X log 10 to get this to work. And so come back to this, do that. So if I give this like a ridiculous number like -2, it's unhappy. If I give it 2, it's unhappy. Or 2, sorry. That's the wrong number. 2 here. All right. Yeah, so what if we put scale X, Y 10 first? That shouldn't matter, but let's see. So let's put this back to like 0.02. Yeah, so that doesn't really matter. Okay, I am going to, if you don't mind, cheat in this for the sake of time. Let me pull up my notes. And let's see here. Let's see what I did. Sorry. I don't like having to phone a friend by going back through my old notes. Okay, we were close. So the x has to be raised to the power. So we have to raise 10, x to the 10, right? So this then gets it to fit through the data, right? So there we go. So again, this, I don't understand this, but I think the data gets scaled before running Geom Smooth, right? And so it's scaling the data and then it's doing the fit, right? And so because of that, because like this value over here on the x-axis is 10 to the -1, but it's really seeing it as -1, right? Like when it scales it, it's seeing this as -1. And so because of that, we need to raise it to the 10 power here, okay? So hopefully that makes some sense. Again, this is not a tool that I use a lot. And so I find that I get better at this stuff by practicing. And so clearly we are practicing. So, okay, so that was for the wild type. So let's go ahead and remove this. And now what we get are all 4 curve fits. And I think what you'll see is that my curve fits and their curve fits look pretty much the same, right? And as we saw by looking at the NLS data up here, right? we get IC50 values. Okay. So I think one last thing I'd like to do here is to, we've got this plot, but it'd be interesting to see like where the data come for panel C. And that's going to come out of the NLS function that we ran explicitly, right? So to do this though, one thing I noticed is like they have one curve fit in panel B for each genotype, but over here they have 3 curve fits for each genotype, right? And so basically I think what they did was they took each replicate from each genotype and they fit the curve to it and then extracted the IC50 value, okay? So let's do that now. So again, that would be kind of like if they did genotype equals GFP and rep equals 1, right? So if they took this data and then they fit it to get these values. So to do this, what I will do will be to nest the data, and we'll do data equals everything but genotype and rep. And so if I spelled that right, we now see that we get a tibble with 12 rows and 3 columns where we've got the genotype, the rep, and the data, right? So like this tibble that's 7 by 2 is like this BFT column and this E-cadherent column, right? That's the 7 by 2. And you'll see that that's 7 rows, right? So we've nested it. And now what we want to do is a mutate. And I'm going to call this fit for fitting the data. And we'll do map. And we're going to map over the data column. Okay. And the data column, we're going to apply this NLS function. And let's get our indenting all right. And so the data isn't going to be period, it's going to be period X, because this data argument, or this data value, is sitting in the .x argument, right? Like if we look at map, you'll see that the first argument is .x, and then we have .f for the formula. And if we're passing parameters to that function, I guess .f is function, not formula. But if we're passing parameters there, we need that tilde. And so I also need another closed parenthesis and another closed parenthesis to close out the mutate. And now what we're getting is more of these problems with the curve fit. So why don't we maybe up this a little bit? So when I did 0.02, it wasn't working with combination 5, and now it's not working with value 6. And so here we just kind of have to, I think, try a few different values. Maybe if I put this to 0.15. There we go. I honestly just picked values around the bottom and the IC50. And so now what I've got is a fit column that is made up of NLS objects, right? So objects generated by NLS. And there's a handy tool for working with statistical data called Broom. I think I've used in other live streams. And what Broom does is it takes like this output, this NLS output that I had somewhere up here, like this, right? Broom will take this and apply and convert this to a tibble, to a data frame, okay? And so as part going out of NLS then, I can pipe that to tidy. And we'll run that. And so now what we see is that fit is a tibble with 4 rows and 5 columns. And so now what I can do would be to do unnest fit. And so this then, you can see, again, like the first 4 rows are for wild type rep 1, where we've got the 4 different terms, the bottom, the top, the IC50, and the hill slope. It's giving me the estimate and the standard error, the statistic, and the p-value. I believe the p-value is testing whether the estimate is significantly different from 0. Okay. So that's cool. Again, I'm interested in the IC50 term. So let's go ahead and do a filter term equals IC50. And so now we've got all our IC50 values. Right? And so I'm going to be interested in the genotype, the rep, the estimate, and the standard error. And I'll tell you why the standard error in a few minutes. But let's go ahead and do select genotype, rep, estimate, std, error. There we go. We now have all our columns, right? So again, we have these fits for each of the different genotypes and their rep. I'm going to come back to that Excel workbook because I believe they had this figure 2C. So, so these are going to be relative. These are relative to the wild type, right? Which is, yeah, okay. So like, let's do that. let's see if we can calculate these relative to the wild type. And okay, so to do that, what do we want to do? For now, I'm going to do a select on genotype and then estimate. Okay, to get that. And then let's do pivot wider. And I would like to do like names from equals genotype and values from equals estimate, but it's not going to like that because it wants one column that's unique. So I think what I'll do is like mutate. Actually, I can leave in, what I can do is I can leave in the rep, and then the rep will be my unique column, right? And so then what I'd like to do is a mutate where we will do C4 equals C4 divided by the mean of wild type. And I guess we'll also do wild type that way too, right? Wild type equals wild type divided by mean wild type. And I'm thinking about this, and I probably want to save this for last because, or I can do wild type scaled. Let's do that. And then we'll do C4 scaled. So my thought was that if I change wild type to equal basically the scaled wild type, then when I do mean wild type over here, this is going to be 1 for C4, right? And that's not what I want. I want it to be the actual raw wild type value. So we'll do C3, C3, and then we need to do the GFP. Okay. Cool. And so that then gets us these scaled values. And then let's do a select for rep and anything that ends with scaled. Okay. Cool, huh? All right, now let's look at our Excel workbook. And what we can see is that wild type, let me make this a little bit bigger. So wild type was, let's just say 0.650. I've got 0.656, 1.59. They've got 1.61. I've got 0.751, 0.742, 18.8, 18.9, 30.2, 30.5, 14.7, 14.8. The values are pretty close. They're not identical, but pretty bang on. And I don't know if the NLS fitter has some stochasticity to it, some randomness to it, but that could account for some of the difference in the curve fit. It's very, very small difference. So I think that's pretty good. I'm going to call that good enough, right? And so again, we're going to want to plot this. And so now let's do a pivot longer. Everything but rep. Do names 2 equals genotype. And then values 2 equals scaled. And I'll say EC. Right? And so we've got that. And then let's go ahead and do ggplot, AES. On the x-axis, we're going to do genotype. The y will be the scaled EC. And then let's do geom jitter. And hide my face. And so now you can see the C3, C4, GFP wild type. And again, that is meant to look like this, albeit in different ordered columns. And they have a y-axis that is on a log scale. So scale y log 10. And again, I've got a jitter, whereas I think theirs is more of like a swarm plot. But again, hopefully they look more or less the same. One thing I do want to point out is that I, in my critique videos, have been on about why we should not be putting bar plots on a log scale. And so a bar plot needs to have 0 on the y-axis. Because what humans do when we look at something like this is we're comparing the heights of those bars. And if it's not at 0, then I am going to get kind of a skewed interpretation of like the height or the area in these bars in a way that we don't when we look at the raw points, kind of like I have over here on the right. Yeah. And so if you then do a log 10 scale on the y-axis like this, you can't have a 0 because log 10 of 0 is like negative infinity. It's undefined. And just to kind of show you what that looks like, if I come back here and I do stat summary, and let's do fun equals mean, and we'll do geom equals call, that I get those columns, right? And maybe I can do it like this, right? So I get the points on top of the bars. Right? And so now if I add on the log 10 scale, so you'll notice that this goes down to 0. I think maybe it was at 0 before. Yeah, I guess it was at 0 before. All right. So if I add the log 10, it freaks out, right? Basically, it's saying we'll go down to 1, but anything less than 1 is going to be a negative value, right? It's because like a log 10 at 1 is 0. Log 10 of 1 is 0. And so anything below that then goes down. And so it's kind of like a, I don't know, I think it's kind of funny because ggplot2 is what's called opinionated. That's like a technical jargon for how Hadley Wickham and the developers of ggplot2 have created how they've created ggplot2. So they make it hard to do things that you shouldn't do, right? So there is a way to get these bars to start down here and to go up on a log scale. I'm not going to show it to you because I agree. I think that's a bad practice and I don't want to waste our time doing that. I want to move into kind of integrating this data in with those curve fits. But there's a way to do it, but it's hard. And so it's opinionated in that like bad things are hard to do. What's another bad thing to do? Pie charts. They make pie charts hard to do in ggplot2. Can you do them? Yes. Are they hard to do? Yes. Donut plots. Yes, you can do them. Yes, they're hard to do. And so if things seem like overly hard to do or a little bit hacky, but they seem like practices that are fairly common, it's probably a sign that we shouldn't be doing it, or we should at least be thinking about why we're doing it, okay? So again, this is a not very cleaned up version of what they have over here with this dynamite plots. I've talked about dynamite plots in the past. I don't think we need to go super far into that, but There you go. Okay. So I'm going to go ahead and grab this data because, and maybe what I'll call this is NLS fit on that, and then NLS fit so that I can have the code, or so that you all can have the code for this. Let's go ahead and bring this back, and then this all works still, right? Okay, so then we have NLS fit, right? We've got our rep and our estimator. And actually, yeah, so looking at this, this isn't exactly how I think it should be done. One of the comments I made in the critique is that like this line plot on the left is fitting the 3 replicates from each of the genotype all in one go, right? And that's what we did up here, right? We don't have 12 lines, we have 4 lines because it's using the variation in the data to help inform the fit. And when we fit the 4 lines, the replicates together for each genotype, we get that standard error value, right? And so that was like, I think I saved it back up here, right? Like this STD error. And so maybe what I'll do, I'm going to go back on what I just did, but let me go ahead and merge these together and run that. Okay, so what I'm going to do is I'm going to redo this for our purposes, okay? And I'll go ahead and grab these lines. And again, this code will all be there when you go to the blog post that is in the link below. And instead of nesting by genotype and rep, I just want to nest by the genotype, okay? So again, here now, instead of having 12 rows, we should have 4 rows. And sure enough, we have our 4 rows. And then we can fit this, and hopefully this works. Yes, no errors, wonderful. And then if we run this, we get our parameters. And so we've got genotype estimate. We no longer have a rep column, but we want that standard error. Okay, and so now we've got our genotype, our estimate, and our standard error. So I'm going to go ahead and call this NLS fit. And if we come back again to our plot, I have ideas for how to incorporate the NLS fit data into our plot. And let's go ahead and clean up our plot a bit to look at more like theirs before we bring in that data. But I think we have everything we need to go ahead and make the NLS fit look a bit better. Max asks, Max from Sweden, welcome. Can we extract the fit parameters in SE from geom_smooth function directly? Not as I understand it. You have to run NLS separately or LM separately from geom_smooth. geom_smooth is not designed for extracting the parameter values directly. You can extract the fitted values, right? So like you can extract what this Y position is for the smooth, but you can't get like the IC50 value. So you'll have to fit the data, okay? And if you're not doing nonlinear, LM or GLM are other, so LM is linear model or GLM I think is generalized linear model. Those are ways that you can fit with linear least squares data, okay? All right, so let's spend some time to make this look more like this, okay? So where to start? Let's start with our colors and shapes and labels and the order. Let's start with the order first, okay? And so we'll do that way back up here with D because D is going to feed into our NLS fit data. And so let's do a mutate on genotype. And we'll do factor on genotype. And we'll do levels equals. And then we're going to do what? We're going to do a wild type, C4, C3, and then GFP. And so that should get the order right. And so then let's come back down to our plot. And here we go. We've got our order, for what it's worth, matches their, excuse me, it matches their order now. Sorry, this is allergy season here in the upper Midwest, and I am not immune, regardless of how much Claritin I take. All right, so now we've got the order right. Let's go ahead and get the color, the shape, and the label right in our legend. And so I'm going to do that in here. I like to put my scale functions together. So we'll do scale, color, manual. Let's see. Can put the plot through ggplot build to get all the plot data though. That's right. So that's the ggplot build would get you, it's basically like running, let me see. I think if I do like str on this, maybe like you get, yeah, it's a mess, but it's only going to give you the fit data, like the y-axis values for the x-axis. It's not going to give you the actual parameter fits. Okay. And should you use Genome Smooth? Yeah. Yeah, I would say it's fine to use. Like we're doing it here. That's a-okay. So we'll do values equals, and then we're going to give it a named vector. So we'll do wild type, C4, C3, and GFP. And so then we need to get our colors. And so the wild type is black. And then I'm going to grab my color meter. And this I'm pretty sure is pretty close to straight up red. We'll get the get the hex code. And now we want this blue color. And then GFP is that purple color. Grab that. And then we're going to want to do labels. And we're going to do wild type, C4, C3, and GFP. And so, again, I think the stylized way they did it, was wild type, all caps. C4 is going to be C4-KO, right? And then C3-KO. And then I think this is C4-KO, colon, GFP, C4. Okay. Yep, and it's upset with me. Oh, because I put a pipe here. Plus. There we go. And let's see. There we go. We now have our red, our purple, our black, and blue. And you'll notice that we have two different legends here. So one is for the color and one is for the shape. And so now once we go in and change the shape, we'll go back to having a single legend. So now what we'll do is add to this scale shape manual. And the values then we need to put in the names. And generally what I do is I kind of hunt for the shape. So I think like 19 is a circle, C4 is the square, I think is like 18, and maybe C3 for a triangle might be 17. And I'm not sure about an upside down triangle, so let's try like 16. And well, no, I got the triangle. But that's a diamond and that's a circle. So the diamond was for C4. So maybe that's supposed to be 16. Well, no, I have a circle for 16. Maybe it's 15. There's a square. And so I'm not sure about the upside down triangle for the C4 KO. with the GFP complement. So I'm going to phone a friend called Google. So let's do ggplot2 shape numbers and aesthetic specifications. I'll go ahead and plop this in this. Yeah. So I think Max also said scale shape manual brings up the list of shapes. And so let's see. Point. Yeah, here. So so we can give shape an integer in the range 0 to 25, and that's going to get us these values, right? So we did 15, 17, and 19. But you'll notice there's no upside down triangle except for 6. And 6, if I put 6 in, is going to give me an open upside down triangle. But I want a filled upside down triangle, right? And so we can also give it names of shapes. And so they have this handy dandy tool. And these shapes will get me, yeah, so there isn't, like in the numbers 1 through 25, I don't see 25 in here, but hopefully that's not the one I want. But these are going to be like the values 1 through 25. So circle filled, square filled, and then triangle down filled. So let's do that. And so instead of these numbers, we can do circle filled, and then C4, as I recall, was square filled. And then we have triangle filled. And let's put this on separate lines. And then this is going to be triangle down filled. And so this again is going to show us the border rather than the fill, but we'll get there in a minute. So now what we've got are our circle, our square, our triangle, and our diamond. And so you might recall, like, this is effectively my favorite symbol 21, where you can change the outer color and have it be different than the inner color. I want them to be the same color. And so what I can do is I can copy down scale shape manual, or sorry, shape color manual, and make this scale fill manual so that the border and the interior of the shape will be the same color. And I then need to come back up to ggplot. We need to also do fill equals genotype. And there we go. We now have a filled square, triangle, and upside down triangle, right? And those might seem a little bit chunky, and that's because, again, it has the border. And the border, we can come back to our stats summary with the point, and we could do like stroke equals 0 to basically make that border non-existent. Right? And so now what we get are smaller sized shapes. I feel like the line for the error bar is too thick. In stats summary, or in geom smooth, we use line width of 0.3. So let's go ahead and use that here with the error bar. So again, there's width and there's line width. The line width is the thickness of the line, and then the width is the width of the hat on the error bar. Okay, so cool, huh? And I'm gonna look at something here. Okay. So one other thing that I think someone else noticed is that the x-axis on mine goes to close to 10 to the minus 3, whereas theirs doesn't go that far. I think they're removing these points. Okay, and that might also be why they and I got very slightly different IC50 values. I'm going to leave it in because I want to include all the data. So 25 is upside down. Whatever. All right. Well, hey, we got to practice with using these named arguments. All right. I was looking at this. I was looking at this and thinking, I wonder what 25 is. I don't see 25. I wonder if 25 is what I actually want. And so it goes. That's fine. So, all right. Thanks for chiming that in. That's great. All right. So we've got our colors, we've got our shapes, we've got our labels. Let's go ahead and, while we're at it, let's go ahead and remove the title from the legend. There's many ways to do that. I think the easiest, because we're going to be using it we're going to be using it anyway, is labs. So if we do like shape equals null, fill equals null, color equals null, we have to set all three of those aesthetics to null to remove the title from the legend, okay? And so now what we want to do are the X and Y axis titles. And so we have on the X axis, we're going to do X equals BFT concentration, and that's going to be nanograms, and I think they did ml to the superscript -1. So I'm going to use Markdown or HTML to do that. And we'll do soup, and then -1 soup. There is like built-in Markdown for superscripts and subscripts. I find that it works inconsistently, and I would just prefer to not have to mess with it. And so I use the soup for superscript or sub for subscript. And I find that that always works. If I'm using geom rich, or if I'm using element markdown rather from ggtext. So we'll have to bring that in. And then we have this y-axis of the normalized surface E cadherin. And so again, this is gonna be bad. So we need to go ahead and bring in library ggtext. Okay, and then here we can add a theme. We can do axis.title equals element markdown. And yeah, I wanted to make sure the color is black because the default theme is gray, and that often will make the text on the axes like a grayish color. It's dark gray, but it's still gray. So that didn't work. So I think we want axis title X. I think we have to be specific. There we go. We now have that superscript being superscripted. Cool, huh? Let's go ahead and shrink the size of that font down. And so let's do like size equals 7. And so that shrinks it down pretty nicely. We want to shrink down also the axis title Y. We'll do element text there. We'll do color equals black, size equals 7. There you go. And it could probably be a smidge smaller. Let's do like 6.5. Something like that. I think that looks pretty good. All right. So let's now turn to the axes. And yeah, let's do the x-axis first. And so you'll notice we've got this scientific notation like 1e to the 0.3, 1e to the 0.2, right? And so in scale x log 10, we can put in our breaks. And so the breaks we're going to want will be like 10 to the minus 2, minus 1, 0, and 1. Tick marks are not scientific. Scientific notation. Sorry. So let's go ahead and we'll do breaks equals, and we'll do, I'm going to go ahead and leave in the minus 3. And yeah, we'll do 1e to minus 2, 1e to the minus 1, 1e to the 0, 1e to the 1. Okay, so those are breaks. And the limits, let's do 1e to the minus 3, and then we'll say NA, and NA will allow it to pick the upper level. So this isn't going to change the labels at all. Doesn't really change much at all. And I think what I will also actually do is get rid of the expansion around the data. You'll notice that there's 0 is right at the bottom on the y-axis. And so we can do that with chord Cartesian. And we'll do expand equals false. Okay, so that fills that out. Okay, but now we want to turn our attention to these labels, which I'm being slow on. All right, so then let's do, maybe I'll move this up. We'll do labels equals, and here again, I'm going to use glue. So I'll do glue 10 soup, and I will then do -3 to 1. Yep. And then we'll close out the soup. Okay. And I think I forgot something. Oh, I forgot the closing thing, and I forgot to put this all in. Forgot to put this all in quotes. All right. I heard somebody saying, "Come on, Pat." So now you can see all my HTML in there. And so now again, we need to do axis text.x equals element markdown. And I think you can kind of see that this font is like a grayish color relative to that. Anyway, I'm going to do the same sizes, the same color and size, because I think like their 10 is about the same height as that B. And voila, we now have our 10 to the powers, right? And maybe on the, so this is 10, 20, 30, 40, 50. Maybe we'll have it go to 50 rather than NA. Right, so we get a little bit of extra space there. And yeah, cool. All right. So the other thing that's kind of cool about this plot is that they have the minor grid lines for the log scale. So let's go ahead and pay some attention to those. So let's start by shrinking down the tick marks and adding the X and Y axis lines. So let's do like axis.ticks equals element line, and we'll do line width equals 0.2. And so that makes those thinner, right? And then let's do axis.line equals element line, and we'll do line width also 0.2. Right, so now we've got our axis lines. That's cool. Those could probably be a little bit thinner, but let's just leave that there. But we want to get in those minor grid lines, right? And I think what we could do is do guide equals guide axis log ticks. Okay. And so this, as it says, lost it, guide axis log ticks, this axis guide replaces the placement of tick marks at intervals in log 10 space. And so it has arguments for the long, the mid, the short. And so that's like the length of the power of 10. And then the mid for it be like a 5, multiple of 5, and then the short for those intervening. So let's make sure this works first. And there we go. We have those tick marks. And again, what we did to get those tick marks was to use within scale x log 10 guide axis long ticks. Now, again, there's like, I'm forgetting what the arguments were. It'll tell us here. So we have long, mid, and short. And these set the relative length of the long, middle, and short ticks. Numeric values are interpreted as rel objects. Okay. And they're used to multiply values of the axis.ticks.length theme setting. So I liked the length. So let's do long equals 1. And then mid, I'm going to do 0.5. And then short, I'm also going to do 0.5. Because when I look at theirs, there's no differentiating, right, between like increments of 1 or increments of 5. And so there we go. We now have those tick marks, right, in between various powers of 10. Cool. All right. Thank you, Tylenol. I think this stuff is pretty cool too. All right, so that's the x-axis looking pretty good. We might come back and clean it up in a bit, but let's leave that there for now. And now let's look at the y-axis. And so we want our y-axis to start at 0 and go up to some value greater than 1. So we can come back up. And again, I like to keep my scales together and somewhat organized. So we'll do scale y continuous, right? And here we're going to do limits, and we'll give it 0 to NA. So let's again start there and see what that looks like. And so now you can see we've got 0 and 1. Noticing theirs has just the 0.5 as the only intermediate value. So let's do that. So let's do breaks 0, 0.5, and 1. Right? So we've got that. And one thing I'm noticing is like these error bars at the top are kind of getting clipped, right? And I don't want them to be clipped. So we could increase the y limit. The other thing we could do is back in chord Cartesian, I could do clip equals off, right? And so now it's subtle, but we can now see those top error bars. Again, this error bar here, or this set of points here, is this here, okay? So yeah, so let's go ahead and shrink down the size of this font on the y-axis. So I'm going to do the same thing for y as we did for x, like the same parameter values, but we're not, I mean, it doesn't matter if we use element markdown, but I don't know. Let's do text. And so now we've shrunk that down. Now let's get rid of the background, and we'll do that with, we'll get rid of the grid line, so we'll do panel and the background. So we'll do that with a panel subset of theme arguments. So we'll do panel grid equals element blank. That got rid of the grid lines. And then we'll also do panel.background equals element blank. And that got rid of that. Cool. So again, at this point, I'm recreating panel B. So let's go ahead, and the legend here is using like almost half of the plot. So what I'd like to do is kind of like what they did here, where they were able to shrink down the font size and the spacing between the font, the legend elements, and then move it into the plot, right? Yeah, so their plot, their Y title expands to the height of the plot, and that is because they have like all this extra white space up at the top that I'm using, right? So I'm trying to use all the space I have available. But I think if I were to shrink this down, like added a margin, it would be the same height as this, right? So if I did like plot.margin equals margin, t equals, let's try 30, 3 and 3. Right, if I did something like that, you can see that very quickly we're getting to be like bang on with theirs, but this might be where I start deviating from theirs a bit. Okay, so let's look at the legend. So we'll come in here and we'll put our legend stuff together. So we'll do legend dot, this is where I always get a little bit confused because there's so many options. Margin, that's not what I want. So let's do legend key dot spacing. Let's try legend key spacing y. Let's do unit 0 pt just to be a little bit absurd. And I don't think that did anything. Okay. Let's do legend key size, and let's make this like 7. So that brought it down. So the key is this symbol. And let's see, if I were to comment this out, again, we had that, but if I did like legend.key.background, legend.key, yeah, I could do like element rect color equals gray. And this then shows me basically the size of the key, right? And so the full size is what's separating the different lines of the legend, right? So if I then come in here with legend keys size and go to like 7, I now see like those squares have gotten smaller and we now have not as much separation, right? So I'm going to leave that on just because it's kind of helpful to see these boundaries. Let's do like legend.text and we'll do element text. Let's do size equals, and let's look at theirs. Again, I feel like this font might be pretty close to that. Maybe it's a little bit smaller. Let's do 6. I think maybe it was a little bit, maybe it is 6.5. All right. That's cool. And so you can now see that we've like trimmed things down. Perhaps there's a little bit more separation. So let's take that up to like 9. All right, I'm gonna split the difference, make it 8. That's cool. And I feel like there's a lot of space between the text and the symbol. So maybe here what we could do would be like margin equals margin. And let's do L equals 0. And that removes the space between the key and the text. We want some space there. So let's make this like 3. I think that looks good. Okay. Now let's remove legend key, the background color, right? So there we go. And we want to move that inside the legend, right? Good eye. So we'll then do legend.position equals inside. And that will allow us to specify where inside the plot we want it to be. So we can then do legend.position inside, and we can then give it a vector of 2 values. So I guess it just put it right in the middle as the default. So I want it kind of like up here. So the first is going to be the X position. So let's do 0.8 and 0.8, and that's where it's going to be centered. Right, so right up there is, let's maybe move it to the right a smidge. Let's try 0.85. I missed 0.85. So over like that. Right. Cool. And I feel like now that we've like broadened the figure, we could of course decide to make it more narrow, but it's kind of nice to have it be broad because then you get to see more of the data. I feel like the caps on those bars are maybe a little bit too wide, and maybe the plotting symbol is too small. So let's alter those a little bit, right? So again, that was back up here in stats summary, where we set the point to 1.5. Let's make it 2. And the width, let's make that maybe 0.1. And I think that's a lot more proportional. I think that looks pretty good. I'm noticing then that this plotting symbol is kind of overrunning the line. And so something we could do with like legend.key.width, we could do like unit, we could do 10 pt. Basically make the key a little bit wider to see more of that line. Okay, cool. All right, so again, I have recreated panel B, albeit at a wider and taller scale to utilize more of that. And what I'd like to do now is bring in this stuff from panel C, right? And so again, we saved that as NLS fit. So NLS fit is like this, right? Where we have the estimate and the standard error. And so in the critique video, something I proposed was to take these estimate values that we have here and draw vertical lines going up to 0.5. I think having 0.5 would be nice also, because again, that's like the IC50. So let's go ahead and add that 0.5 line. And I'll put that in the back. So we'll do geom h line, and we'll do y-intercept equals 0.5. We'll do color equals gray. And let's do line width equals 0.2. And then I'll do line type equals dashed. And there is that 0.5 line. Okay. Cool. All right, let me just take a pause and take a drink. And again, just a reminder, if you're interested in getting my help on a one-on-one basis to think about your own data visualizations and trying to make them more effective, by all means, reach out to me by email. It's probably the easiest at pat@rifamonis.org. I'd love to get to know what your needs are, the needs of your research group, and how I might be able to think about, take what I do here on the YouTube channel and apply it to your particular needs, so that I'm not critiquing your video. Well, it will be, right, to say that this is a great plot. And actually, I think this plot, panel B, is really good. There's very little negative that I had to say about it, just kind of things that I wanted to experiment with. So if you would like that kind of treatment on a private one-on-one basis, feel free to shoot out an email to me. All right, so what I'd like to do now is try to draw a colored line coming up from the x-axis showing where the IC50 value was. And I think you can kind of already see where the IC50 values are just by putting in this dashed gray line. But let's put in the fitted value. And so to do that, I am going to come back up here, and I think I will put it, well, it's going to be the same color, right? So it doesn't really matter where I put it. So I'm going to put it after like the smooth, and I'm going to do geom segment. And we're going to do data equals NLS fit. And then we're going to do AES for our mapping. And the geom segment requires like an X, an X end, a Y, and a Y end. So if I just give it X, then that's going to use the same for X and X end. And so this is going to be from the NLS fit. Let me remind myself what that is. I think that's going to be estimate, right? So I'll say estimate. And then my Y is going to be 0. And my Y end is going to be 0. And then my color is going to be genotype. Okay, so if I add that in, I got nothing. That was surprising. Did I get an error message I didn't see? Genotype, estimate, standard error. I wonder if maybe it didn't load. Nope, it's there. All right, for some reason it didn't load. Geom segment, NLS. Oh, because I made Y and Y end at 0. I'm getting tired. Okay, let's make Y end 0.5. How about that? There we go. Now we have our IC50 values drawn up to the 0.5 line. And I think this shows the IC50 values, but I can see this adding confusion. I think I'm a little bit confused as well, because it's odd that like these lines don't intersect 0.5 where the curve does. And I don't know why that is. I think it's perhaps because like there's variation in the data. We know there's a standard error, but again, if I look at NLS fit, like these standard error values are pretty small. But yeah, so I don't know that that's going to work. Yes, thanks, John. So I'm going to try a different approach, and hopefully this doesn't take too long. So I'm going to go ahead and I'm going to comment out the geom segment. I was really hoping that that would work better. And I'm going to go ahead and save this as smoothed plot. All right. And let's take that NLS fit. And let's pipe this to ggplot, AES. On the x-axis, I'm going to put estimate. And so what I'm seeing is on the x-axis having my estimate values, my the BFT concentration, right? And on the y-axis, I'm going to make it 1. Or, yeah, I'll make it 1. How about that? I guess I could also make it genotype. Let's try that. That's fine. And we'll do color equals genotype, and then shape equals genotype, and then fill equals genotype. And then I will do geom point. And then let's see what that looks like. So that gets us this, right? So what I'm thinking about is having a strip at the bottom of my curve fit that I might assemble with patchwork to show the IC50 values, right? So we'll see how this goes. So let's go ahead and grab basically these scales. So the scale X, from scale X log 10 down through scale shape manual. And I will also grab the labs. So let's plop that in here and get our geom point added. All right. And let's tab this over a smidge. All right. And I feel like it is upset with me for something. I think I forgot the scale X log 10. Okay. There we go. Oh, and this scale Y continuous, probably don't really care about. Okay. So now let's see what this looks. It should have a plot that looks a lot more like what we had if I didn't put in the plus sign. All right. There we go. And there we go. So now we have some work to do. And what I'd like to do is bring over a lot of the theming, right? And I'm going to wait on the theming. So let's go ahead and remove the Y. And actually, I'm going to make the Y IC50. And that IC50, I believe, needs to be a subscript, the 50, right? And yeah. Okay. So it looks rough, I know, but hang on. I'm also going to turn off the legend, and I'll do that back up here in my geom point. I'll do show.legend equals false. Okay. So these are going to be like my IC50 values. And so again, picture this as a strip underneath my curve fit. And I've already saved this up here as what? As smoothed plot. And this I'm going to call my IC50 plot. Okay. And we're going to add those together, and I'm going to do that with library patchwork. And so, again, that's not what I want. I want one column and 2 rows. So we'll then add to this plot layout. And part of the reason I'm doing this also is because I want to practice more with patchwork. And so getting a little bit more comfortable with these functions and using theme functions between them. So plot layout, we'll do ncall equals 1, and we'll do heights equals c 0.8 and 0.2 as a starting place. And There we go. It doesn't look like much. All right. So again, we have the fit on top and then these values on the bottom. I would like to have a common x-axis for both of these plots, right? Because these are the BFT concentrations. And so to do that, I need to get the formatting of the x-axis in both plots to be the same. So I'm going to then go ahead and do theme with that ampersand. And then I'm going to bring over things from up here that I would like to have down below. And you know what? Maybe I will grab all this stuff except for where I'm messing with the legend. Okay. So I'm going to go ahead and cut that out. I'm going to rerun that to load the smooth plot. And I'll plop this in. Now let's see what this looks like. Okay, so now you can see much more similar styling. And to gather those x-axes, what we can do in plot layout, I think, is axes.collect. So that's the title. And I'm noticing that my x-axis on the bottom doesn't start at 10 to the minus 3. It starts before that, right? And I think that's because I used chord Cartesian back up here. Yeah. So I'm going to go ahead and grab that, copy it, and paste it into my IC50 plot. There we go. We now have a common x-axis for both plots. And what I'm seeing, though, is that it removed the expansion from the y-axis and the x-axis. And perhaps I only wanted to remove it from the x-axis and not the y. So let's come back up here. And so I did, let's see. Maybe I will turn this off, and inside of scale x log 10 then, maybe what I'll do is expand equals c 0, 0. And so that will turn off the expansion only on the x-axis. And there we go. Now we have a common x-axis for those. We might want to have, though, a solid black line at 0 for the upper plot. So let's go ahead, back up here, and we had a geom H line already. And so I could basically vectorize everything, but to have one statement, but let's not do that. Let's do black, and then line type solid. Reload that all. And so now we've got that black line. The one downside of this is that we don't have the tick marks. I don't know. I think that's, we'll see. We'll see what we think about this in the end. I don't think that's a deal breaker. I think that's kind of okay. And I now would like to, I'd like to get rid of the y-axis on the fit plot. And so I have this like axis title y and axis title y, axis text y. So I'm going to go ahead and maybe I'll also make like axis line x, x. And I'm going to grab, I'm going to copy this, and I'm going to remove the y-axis stuff. And I'm going to paste what I copied back up here into the plot fit and only show, only change the y-axis stuff, right? So we're going to show the y-axis for the upper plot, but not the bottom plot. So let's see if this works now. All right. And so I have stuff. So I need to turn this off. So now to turn that off, I'm going to come back up to my IC50 plot and do theme, and we'll do axis dot text.y element blank, axis.tix.y element blank, and then I'm going to do axis.title.y element markdown. All right, so there you go. We now have that. And great to have you, Ali G from Turkey. I will definitely be posting this video, posting this code. When I'm done here in a few minutes, down below in the description, I will provide a link to a blog post where you can go to get all this code, because I know it's a lot, but yeah, thank you. So let's go ahead now, and this IC50, I want to shrink it, and I want to turn it 90 degrees. So I think the titles up here, this axis title Y, maybe I'll copy this, right? The black and the size 6.5, and I'm going to plop that into here. All right, and so now we've got that smaller IC50. And now what I will do is my axis title Y is angle equals 0. It's either 0 or 90. I can never remember. And let's see how we look. There we go. We've got our IC50 there. And what I think we could do is bring the IC50 over a bit, because we don't have all the text there. And I think this is being left justified on the left side of this title. So if we bring the IC50 over, then we should get more space. And so let's come in here, and that was this title, right? And we'll do margin equals margin. And maybe I'll just set them all to 0. So that brought it in a bit, right? I think this, though, is like justified at the top rather than the middle. So let's try, it's either vjust or hjust. Let's do vjust equals 0.5. I think it's vjust, but there we go. That moved it down a bit. And so now let's move the right margin to do like -10. And so we can see that that is pulling the plot closer to the title. And so I made that -10. Let's make it maybe -5. And I think that'll be good. There's quite a bit of margin around both of these panels. And so there's margin around the panels, and then there's margin around the entire patchwork. So to do the panels, we could do plot.margin equals margin, and that'll turn off all of the margin, right? Which we see here is putting our bottom plot right up against the bottom. So if I make like the bottom 10, oh, that's a big margin. That's a lot larger than I thought it would be. So to change the overall layout, we could do plot annotate, and we can do then the argument would be theme plot dot margin, and then we could do margin, and let's do like 3 all the way around. And I think I think I've got plot annotation, not annotate. Okay. So that's being very weird. So I think this plot margin is behaving odd. So let's turn that off. And I think what I'll do instead is come up here, and for each of the 2 plots, I'll do theme plot.margin equals margin, and then let's do like 0 all the way around, but so that it goes top, right, bottom, left. So on the bottom, let's put like 5, And then we'll do the same thing for the IC50 plot. And here, let's make that 0 all the way around. Like that. Yeah. So, one thing we don't have are the confidence. So let me know what you think of this layout. Yes, I see someone saying geom error bar. Yes, so let's go ahead and do that. So again, that would be in our IC50 plot, right? And so we'll come back up here and we have geom point and we'll do geom error bar. And my understanding is that geom error bar H has been deprecated. Oh, I have to spell it right. I thought it had been deprecated. Maybe not. Okay. Yeah, and so we're going to do, let's put this up here. So do y min, or sorry, it's going to be x min equals estimate minus std error, and then x max equals estimate minus std error. And I'm going to do 2 times the standard error. People could probably debate what we should do. And I'm getting some nasty grams. Yeah, so geom error bar H was deprecated in ggplot version 2, ggplot 2 version 4. So we could, should be able to use geom error bar. I have to write it to the file. And that is weird. And I think X max, I did minus on both of them. Okay, plus. All right. There we go. So we have those confidence bars. And this is showing up as a legend. So let's go ahead and make the lines a bit more thin. And we'll do line width equals 0.2, which is, I think, what I used up above, right? So back up here, we used line width of 0.3. I'm gonna copy this. And we did size 2 stroke 0. So if I come back down here, so that's that. And we then did stroke equals 0, size equals 2, I thought. And then here we also want to do show legend equals false. And we're coming to the end here. There we go. And those error bars are, they don't have the caps on them. And I wonder if that's because my width is 0.1. What if I make that 1? There we go. So like so. Right? And so I suspect that if I like drew up from that, yeah. So that then is going to incorporate, that is going to like, at least at the upper confidence interval, intersect with the line. I don't know. So I would propose this to you as an alternative to this, okay? Where in mine, I don't know that it's probably not the best. If I thought about it more, I think we could maybe come up with some alternative approaches. But I like having the IC50 make it clear that that's the BFT concentration, making it clear that the IC50 comes from the plot above it, right? As it's currently presented in the paper, you have to kind of dig through the method section, actually, I think, to understand what fold resistance is. And Here, I'm not presenting fold resistance. I'm presenting the IC50. And I'm not going to do it here, I don't think. But there are, or maybe I will. I don't believe there's statistics either. Like, I think that this purple, because of the way they did it by fitting the 3 lines separate from everything else, is actually significantly different from the C3 and the wild type, right? And I think that's fine, right, for it to be different. I think the point of this complement was to say that like they basically restored resistance. And maybe they didn't fully restore the resistance, but it's pretty close. And maybe that's because of the GFP. Who knows, right? And so the downside, one of the downsides of my approach, I think, is that we don't see the fold resistance, right? That we think that, well, this is right at about 1, and this wild type is down at about 2, 3, 4, 5, like 5 times 10 to the minus 2, right? So we have to do a little bit of work. The other thing I'm noticing is that the order here is different. And so maybe one of the last things I'll do here is let's go ahead and flip the order of the axis, of the y-axis. And so I'm going to do that. I think I can do that actually in scale y discrete. And I think, can I do, no. Here, let's do it as a factor. That's easy enough. So we'll do mutate genotype equals factor genotype levels, and then we'll reverse it, GFP, C3, C4, wild type. And there now we have the same order from top to bottom that we have up here in the legend. Okay. Another way, Mark says, another way to show is the confidence of the cloud of the line of best fit. Yeah, so the problem with Geom Smooth is that it will not, it won't show the standard error for the NLS model. There are certainly ways that you could incorporate that to show the model. In terms of, Ali G says, it depends on the multiple comparison test. So I don't know if there's actually a multiple comparison test to be done here because everything's getting compared to the wild type. And I think that's pretty clearly an a priori test. I have 2 line width values for Geom error bar. Do I? Geom error bar. I do. Good eye. And I think it's supposed to be 0.3. Yeah. That's cool. Thank you. Good eye. So if I took like the NLS fit, and I think what I was also thinking would be that like I could take NLS fit and I could do like mutate ratio to wild type and say that that's going to be estimate divided by, it would be like first estimate, right? And so now what we get are the ratios to wild type. And what I would propose would be then like in the text of the paper, you tell us the ratio of the wild type, of the ratio to the wild type, right? Something that I found, and this is, I promise, the last thing I'll do, is this cross-validated, it's like Stack Overflow post on comparing various parameters. And here's the solution, right? So basically, parameter 1 minus parameter 2 divided by the square root of the standard errors of the 2 parameters squared and summed, right? And then that's a z-test. And so what we might do would be like NLS fit, and let's do filter genotype equals wild type and genotype Sorry for going long on this. I appreciate you all watching. If you're still tuning in, it's great to have you. And so if this is our NLS fit, and I need two equal signs here, right? Oh, it's upset with me. Why are you upset with me? NLS fit, genotype. Oh, duh. Or, right? Okay, come on, Pat. You can do this. And let's see. Yeah, I'm getting tired if you can't tell. Let's pivot this wider. So we'll do pivot wider. Names from genotype. Values from equals estimate and STD error. And I forgot the C here. There we go. So we can pivot wider, right? Like that. And then what we can do, let's do mutate Z, and we'll do the estimate of the wild type. Oops. Estimate of the wild type minus the estimate of C4. And I'm sure there's a much more tidy way to do this than I'm doing it, but my brain is tired, and I think I've gone on far too long already. So we'll do then divided by SQRT on the standard error of beta 1 squared. So again, that's going to be standard error of wild type squared plus the standard error of C4 squared, right? And so that gets us a Z value that unfortunately I can't see. So let's go ahead and pipe that to select Z. So that gets us like minus 8.5. And I think that's because maybe I could flip the order here and get a Z of 8.5, right? And then what I could do, so I could call this C4, and I think what I would then do is PC4. You can test that with a Q norm. It's either Q norm or P norm. Let's try Q norm. Nope, it's going to be P norm. And do 8.5. And I want to do a select on Z, C4, P, C4. And we get that, but this should really be like 1 minus that, or I think there is a lower tail equals false. And I forgot my select, which we get there, right? So then this becomes my p-value for the C4 relative to wild type, right? And I could do the same type of thing for C3. If I come through and modify C3 for all this, and that doesn't seem right. I think I forgot something. Oh, why did I put, okay. That's not right. That should be Z4, C3. All right, there we go. So our p-value is 0.658. Comparing C3 to the wild type, and our C4 to the wild type is mighty small. And then the final comparison would be the GFP. So let's do that real quick. Thank you for bearing with me here. I'll give you a special prize for that. And so then bam, bam, bam. And so again, this is a very small p-value. Even if you were to correct for multiple comparisons, multiply that by 3, it's still going to be less than 0.05. And so again, I think, I'm not a statistician. I would encourage you to talk to a statistician if you're doing this type of work, but I think it is a more reliable test to get the parameter value from the fit with the standard error when you're fitting all of your replicates together, and then do some type of comparison of those estimates with the standard error versus what they did here, right? Like, I don't think the results, again, don't change. Like, the story doesn't change, but I think the interpretation is a bit more precise like this. I also think, again, more closely linking the IC50 values with its variation to these dose response curves is, I think, I don't know, just an easier way to interpret the data. The downside, of course, is that it's not as easy to get out the log fold change, or the not log fold change, the fold change relative to the wild type. And maybe for that, what you could do is off on the right here, you could put like the fold change relative to wild type, right? Like that might actually be helpful. Like right here, it's like fold change, and below that have those 3 numbers. And before I post this, I might do that so that you can see what it looks like. But this is going on long enough, and I am sorry for going on so long, but thank you very much. And so Mark, your comment about method equals LM, SE equals true. Yes, that will work for linear model, but not for NLS. If I, just to kind of show, so let's see, I have, where'd you go? Geom Smooth. If I do like SE, well, actually by default, SE is, oh, I have it being false here. Come back. If I make this true, I'm pretty sure it's going to complain. Yeah, so this is mainly coming from the SE equals true, right? And so when you're using method equals NLS, SE has to be false. But if you're using LM or GLM, you can incorporate the standard error and get those clouds. Otherwise, you're going to have to extract it from the NLS objects itself, okay? Very good. Well, I need to change the second squared value. Oh, yep, this is C3, and this should be GFP. Thank you. Again, if I wrote this in a tidy way, aha, it is not significant. Thank you for that. That is very important. Okay, so I stand corrected. Unless I've got some other typo in here that I'm not seeing. Oh, no, this should be standard error GFP. All right. Okay, now let's try it. No, it is still significant, even with the other, with the correct standard error. Okay, so again, I'm going to end there because I am getting fried. If you want, I will, if you want to kind of look at my updated code, I will try to put in a little indication here of what the difference in IC fold, or the fold resistance is relative to the wild type over here maybe. I don't know. Let me know what you think of this. The suggestion also of having like the vertical lines with like the cloud around it is intriguing. I kind of don't know what that would do in cases like this where we have the black and blue that are so close to each other. I think it works nicely when they're not close to each other, but when they overlap, I'm afraid that might start looking kind of weird, but I don't know, it's worth trying. I encourage you to give that a shot yourselves. You can do that with probably like Geom Rect or something like that. But anyway, let me know what you think of my alternative approach down below in the comments, and we can keep that conversation going. Be sure to check out the code that I'll be posting. And again, if you would like help with your own research, shoot me an email and we can set up a time to kind of talk about what your needs might be and what kind of services I might be able to offer for you and or for your research group. All right. Well, thanks again for tuning in, and I will see you next time for another episode of Code Club.